Welcome back everyone. I'm Sri Tanesh, and in this video, we're going to talk about FFT transform. Basically, FFT transform is not a method as such. It is a algorithm to reduce the computational complexity of discrete Fourier transform (DFT). Discrete Fourier transform has a high complexity of n square complex multiplications and n into n minus 1 complex additions, whereas FFT has a computational complexity of only n by 2 log n complex multiplications and n log n complex additions, which is way better in any way imaginable. So what we do in FFT is that we take DFT of signal, we separate even indices components and odd indices components, and we get therefore we get two DFT signals of half the length, which is way better in computationally. So here we see 2 are the even components and 2 are plus 1 the odd components are taken up, and the critical factor W and K is separated, which gives us the two what to say two DFT signals of half the length and by 2 the length with the odd components multiplied by critical factor. The critical factors properties of symmetry and periodicity are greatly exploited here in FFT to reduce the time complexity even further. So the even components are taken to be g of k and the odd components are taken to be h of k, and then they are further broken down into even components and odd components in themselves until the length reaches to be 2. An important point to be noted in FFT is that it requires the length of the input signal to be in powers of 2, that is the length of signal to be 2 power k k-Grom's natural numbers. If it is not, we do zero padding to get the length of signal to nearest 2 power k value. Let's take a look at the AMM signal. The AMM signal is that in the given signal they are both respiratory and PPG signals. We have to isolate out the respiratory signal and find the respiration rate. We do this. We do the process by both. We do this by both Arduino and MATLAB. Let's take a look at the Arduino code. Arduino has a separate FFT library, Arduino FFT, for computing FFT fast Fourier transform. We create an FFT object, and here the given length of signal is 300, so the nearest 2 power k number is 512, so we take samples as 512, and I'll see what VReal and VImage, X and Ximage are. Well, the VReal and VImage correspond to vector V, so the signal V, which is the IFT. Since this Arduino does not have a Arduino does not have a facility to represent complex numbers, we take real components of IFT in VReal and imaginary components of signal FFT, and that is a V signal in VImage. Here what we do is we find the mean and we subtract the mean, get zero mean signal, and then we compute a fast Fourier transform signal. FFT library has an inbuilt function of FFT.compute fast Fourier transform for FFT forward, for FFT and FFT reverse for IFT, inverse Fourier transform, and therefore we get the fast Fourier transform signal in VReal and VImage. These two give VReal plus J into VImage gives us the actual fast Fourier transform of the given signal. So let's take a look at that. This is the magnitude spectra. As you can see, there are two peaks, this and this. This low peak corresponds to respiration rate and this high peak corresponds to heartbeat, because we know that heartbeat has higher normal frequency than respiration rate. So to find out this frequency, what we do is in order to deal with interference, we isolate out this part. Let's say from the normal band of respiration, from indices 2 to 25. Like I said, we're gonna take out the indices 2 to 25 and store them in X x there and x image, we're gonna find the zero minimal signal, and then we're gonna perform inverse Fourier transform. So let's take a look at that. Respiration rate. This is the respiratory part of the signal. The parameters is 2 to 26. Since I do not have an Arduino port connector, I cannot run the code right now. But the respiratory rate we get through this is 21, about 21 point something, to 20.1 something. So let's take a look at MATLAB implementation. MATLAB also has the same algorithm. MATLAB also has the same algorithm except for the well, nothing. I think MATLAB also has the same algorithm. Here we find the DFT, first maximum, and etc. For the respiratory rate in MATLAB we get 16. So maybe because of the in MATLAB we get 16. Sorry about that. In MATLAB plots, this is the magnetospectral signal, autocorrelation, isolation, and this. In MATLAB we get 16. Thank you.